Good. So now let's move on to the next talk. The next talk will be given by Adam Norton from University of Massachusetts Lowell, and he will tell us about remote experimentation of manipulation. So, Adam, please go on. Do you have?
Thank you very much. Yes, let's see if it will show.
Perfect.
Let's see. Wonderful.
Thanks.
All right. Thank you very much. And thank you to everyone who has presented so far. I've been taking a lot of screenshots during the other presentations. So again, my name is Adam Norton from the University of Massachusetts Lowell, and I'm going to be giving a talk to give an update and an overview on a collaborative project between UMass Lowell and Oregon State University called Remote Experimentation of Manipulation for Online Test and Evaluation, or an acronym of REMOTE. So as has been articulated through several of the presentations today, we all face very kind of similar challenges in benchmarking for robotic manipulation. A lack of repeatable tests with robust and nuanced metrics, several mentions of ways to add noise that can be actually expected out in the real world. Some methods of doing this are to have more detailed metrics aside from just efficacy for success and failure, but also additional sensors and ground truth sensing into some of these apparatuses. But also more data collection is needed to evaluate the actual robustness of some of the solutions and to make them more accessible to people. We have a lot of data sets that are available out in the research community, but they're all in different formats, and evaluating the either generalizability of a solution or transferability of one capability from a system to another requires a lot of different robot hardware. Not everybody has the budget for a large multitude of robot arms. And we want to lower the barrier of entry into performing grasping and manipulation research. So with all of those in mind, we have an overall project goal of establishing remotely accessible robot test manipulation facilities. And doing this with a combination of test stations, which includes associated objects and metrics to measure the performance on those test stations, which will allow for repeatability and consistency of each of those tests. Highly instrumented test stations consisting of sensors, cameras, and the ability to replay some of those values back as part of your data collection. As well as a large-scale data capture method that is a searchable and a consistently stored and formatted set of collected data that can help drive comparison and benchmarking across the community. Seeing this either as raw data, analyzed data, summary statistics, and labeled results for more interpretation. Additionally, considering the interface that's needed for specifying those tests, visualizing the tests, replaying them, and doing this with components that are remotely accessible and modular so they can be changed in and out. So kind of a snapshot of what the system, kind of quote unquote looks like is summarized in this image on the right here. This shows several different test stations, of which I'll go into a little bit more detail with a few example test stations to try to illuminate the way that the project is supposed to be functioning. But essentially, it's broken out into 4 parts. There is the test stations that each of the robot systems interact with and all of their related setups, metrics, and related sensors. The hardware, or the different robot systems that are available to use as a part of this test bed. The software components that drive each of those tests, and the data that is collected. So from a high level, the kind of vision for this project is from the user's perspective. Their experience would include downloading or referring to a software framework and developing some components of their manipulation algorithms, of whichever parts that they're interested in. And first, testing those virtually. We've seen a couple different assets that have been mentioned throughout this workshop. So not necessarily talking about creating our own virtual simulation environment, but certainly something that we can leverage so that things can be run in simulation before they get run physically. These physical tests would be scheduled at a desired date and time, sometime in the future, where they can kind of run their tests remotely, come back, and when the tests are done, collect the results. And as part of that, selecting which test station they want to run, which hardware, under which conditions, etc. Uploading their code using the software framework, wherein some code checks would occur for compatibility, conformity, whatever the other kind of styles and rules that we set as a part of the project. And then when the desired date and time are set, those physical tests get run at Oregon State University or at UMass Lowell, because we'll have test beds set up at each site. At the end of each test, labeling and storing them such that they can be accessed via the online directory, but also played back for users to reconstruct what happened during one of those tests. Now, I should point out that this project is it's a multi-year project through the National Science Foundation. We're in year 2 of it right now, so this is not a fully completed system, but I just want to kind of give everyone here an update as to where we are and kind of where we're going. So in the current setup, we have our test stations and artifacts that span both grasping and manipulation tasks, those for repeated grasp testing or shelf picking, kind of modeled after the ACRV picking benchmark, and using a variety of different objects within those 2 grasp setups. On the manipulation side, looking at more kind of task-based performance, such as door opening, drawer opening, or small parts assembly, taking advantage of the NIST assembly task board. Now, each of these test stations has their own kind of special requirements for what elements we want to be able to automate, what elements we want to be able to measure during performance, and what other types of tasks are able to be performed within each test station. So in the repeatable grasp testing, our intention here is to allow for objects, physical objects, to be automatically swapped in and out without human intervention, and have their positions reset after each grasp attempt. And I'll show an example video of that in a moment. For shelf picking, while the setup of the shelf itself is not automated, we do implement a variety of sensors so that we can measure which object is being interacted with, the timing and objective measurement of when that object is lifted out of the shelf or placed elsewhere, as well as the arm entrance and exit into the shelf itself. For the objects that are available, we utilize some basic shapes, some of these sensorized objects from the New Dexterity group from New Zealand, the YCB objects, as well as the adversarial objects that came out of the DexNet effort. For the door apparatus, automating when the door is closing after it's been grasped, measuring any contact that is made with the handle via some touch sensors that are embedded in the handle, as well as the measurement of the door angle. Similarly for the drawer, except now we're talking about the drawer depth when it's open as opposed to the angle. And then on the assembly task board, using a vision-based method to objectively measure when certain parts are fully inserted or fully removed for assembly and disassembly tasks. So there's a variety of different tasks here and trying to leverage what we can from the research community. Now, for the repeatable grasp testing, it's just a quick kind of video demonstration of the differences between what it is we're trying to solve with the automated grasp apparatus itself. So on the left is a series of videos that were constructed for a different project where we were doing some grasp testing comparison between 2 different types of grasping algorithms. Now, what you'll see every couple seconds is someone's hand go in to reset the object. And this actual test took quite a long time to run because there were multiple repetitions in order to really test the robustness of each of these solutions in different environments. So because of that, the manual resetting was quite laborious. And also the resetting of the location and the orientation was approximate. There was no external sensing that was used to actually evaluate the position that the object was in. This was purely just us with marks on the table. Took quite a bit of effort. On the right-hand side is a video of one of the prototype sets of the grasp reset mechanism. Now there's a couple of white pieces of paper that are blocking some elements underneath just for visual contrast, so it's a little easier to see what's going on. But underneath all of that is a mechanical framework that is pulling the object back into place and then actually rotating it in place so that you get the same orientation every time you go to grasp it. Now, granted, this example is a cylindrical object, so the rotation of the orientation is maybe a little harder to interpret, but this could be any shaped object that has this particular shape underneath that allows it to be pulled back into the center and then rotated to be grasped again. And you can see how this type of test could be run for hours at a time to collect a spread of performance data. In this, it shows a couple of April tags that are positioned on the top of the object, as well as actually a few on the robot's fingers, kind of experimenting with some of that external sensing so that we could get a better understanding of the ground truth of exactly what occurred during that test. Now, I don't have slides for all of the test stations, but they are in various forms of development. And we're here today on this workshop to kind of get an understanding of what it is we might be missing and the kind of improvements we want to make moving forward. So I'm going to cover a few of the other aspects of the project. The hardware that we're currently utilizing is trying to span between kind of lower accuracy, more assistive tech robot systems such as the Canova Jaco 2, up to a higher accuracy but more collaborative system, say through the UR5E, up to a completely industrial system for the ABB 1200 or some other type of similarly industrial arm. We're also considering integration with the Fetch mobile manipulator, given that as part of running this test bed, changing some of the apparatuses in and out, depending on the type of tests that need to be run, can either be part of some of the manual process, or we can take advantage of the mobility capabilities of the Fetch system to do some of that translation. And there's also a couple of different grippers that we are considering and trying to use these in ways to make them kind of interchangeable to set up different types of tests, and more to be determined. Now, the software components of this project, there's quite a few, and this is a very large team that is working behind the scenes to put all of these elements together, spanning from the control of how a test is constructed, which I'm going to go into a little bit of detail about on the next slide, simulation elements. There's a couple things that were mentioned during the workshop today I've taken note of, particularly things like RL bench, and some of the other elements there that we might be able to take advantage of. The actual evaluation of the test stations, each of them with their own measures and metrics, depending on what the test is and what metrics we want to derive. Ground truth measurements for determining the locations of objects or the locations of the robot in relation to those objects while performing the test. The data capture and labeling of that data so that it can be stored, visualized, and replayed. And then, of course, the user interface, the actual input mechanism that is used when the system is utilized. Now, for the test flow control, this is something we've spent some time in the past year starting to really try to formalize. And what's shown on the screen here is a table that lists the different stages of any of the manipulation tests that is going to be run as part of the remote system. So going through those stages, it is intended to set up a flow that can be applied to essentially any sort of grasping or manipulation task that could be done, multiple repetitions over and over. So starting in the top left box at the reset stage, this is basically your kind of initial kind of stowed position where the robot is not really engaging with the workstation, and the test station itself is back to kind of a neutral position. The robot goes into position, again, from kind of a nominal place, but somewhere where it can then later get into a position and approach the task that it's going to perform. Grasping, meaning it is actually performing some action with its end effector to interact with that test station. Manipulating, meaning, in this example here, actually opening the door to a specified angle, or if it was a grasping of an object, moving it into another part of the space. Releasing at some point, whether that is part of a placement task, or in this example, just pulling the door open to a specified angle. And then a few other checks based on if it was a failed manipulation, maybe we need to reset that equipment in order to attempt it again. Or if it was a successful task, retreating and then returning back to that reset position and analyzing the data. So this is still a work in progress, but we're trying to define this in a fairly agnostic way such that if other types of tasks get integrated into the test bed, we can apply this flow control onto those tasks. And essentially, as part of the functionality of the system, there will be some baseline code that will allow each of the robot systems to perform different elements of this flow control that then can get overwritten by the user based on the types of capabilities they want to evaluate. If they're uploading a custom algorithm for determining the location of the door handle, for instance, then the position and approach stages will have different outputs based on the code that they upload, and then it'll perform the rest of the task. We're trying to design this so that it can kind of be a pick and choose which elements of the flow control you want your capability to try to perform the task with. So there's obviously a lot of moving parts with this project, and I'm only touching on a few of them here for the talk today. But for the time being, we are finalizing all of our different test station designs and kind of getting all of their hardware and standard sensing interfacing ready to go, and experimenting with different local computing options like Raspberry Pis, and getting all of that kind of raw structure developed. We're developing all of our base functionality so that we can start to actually run some manipulation solutions at each test station, and starting to explore more concretely our options for uploading user code and performing those different code checks. But what we want feedback from the user community on is how relevant are the tasks that we've identified? Are there additional ones that we should be considering, such as grasping from a pile? I know that's one of the tasks that's been mentioned in some of the talks today, as well as the subject of the cloud robotics competition that occurred last year. And what other ground truth data would be useful? Are there other needs for data collection that could be useful for a system like this? What is the best method for users to provide their particular algorithms and capabilities? I know in the cloud robotics competition, they utilized Docker images that were uploaded. But is there maybe any advantage to reducing that into uploaded code that has to follow a certain style or communicating with certain topics? So those are some of the open questions. Any other feedback as we continue to develop this project is very welcome. And like all the other talks that have been mentioned today, I'm just the messenger representing on behalf of the project. And while these are the 4 PIs related between OSU and UMass Lowell, I do want to highlight all of the staff and students that are shown in this blue box here that really are doing all of the legwork in putting this system together. It's a very large, multidisciplinary effort between mechanical engineering, electrical engineering, computer science, and they really deserve all of the credit there. So again, this is a National Science Foundation supported project, and thank you very much for your attention.
Thank you very much, Adam, for the great talk and really interesting initiative. Is there any question from the audience? You can raise your hand or place the question on the chat. In the meantime, Adam, maybe I missed it. Can you explain a little bit how would the person that wants to use this facility interact with you guys? So should you send the code and then you execute the code, or how did it work? Do you have defined already the software framework for that?
Yes, so the kind of final structure of the framework is still in motion, and the actual interface that would be utilized by a user is still kind of an open question, but it would involve some online interface. First going through some type of scheduler to determine when it's available in the test that you want to run, and then we're still kind of figuring out how then would someone provide the code that is to be run. If it's uploaded through, maybe it's a file through like an FTP upload, or if there's some other type of service that we can use. We're still kind of figuring that out to see what would be most effective, because there's also other things like security concerns and things like that we'll need to consider.
Perfect. Thank you very much, Adam. Thanks again for the very nice talk. And yeah, looking forward to see you. So there is actually, before we move to the next talk, there is one more question from Martin Rudolfer. Is it intended that the framework will be continuously available to the robotics community after completion of the project, or will it be used for a particular competition?
So the intention here is that this is, we use our NSF award to get the service set up, and then from there it is available into the future. There will be some type of pricing model associated. Our intention is to keep this very cheap, but just for keeping the lights on and maintaining our connectivity. So some of that is still to be determined, but we are doing this for the long haul.
Great. Thanks a lot, Adam, once more. And thanks for this very nice initiative.